Could we switch the screens, please?
It's espera. Please, just 1 second, just coming.
Okay. We're going to get into what basic statistics to actually collect and what do they impact. When you're gathering table stats, by default, statistics we pick up are things like number of rows, number of blocks, average row length, number of distinct values. So every time you heard me use the term NDC, this morning NDC meant number of distinct values. We also get the number of nulls in a column. Just using these basic table statistics, you could start to write a pretty effective optimizer. Think about it, you know. If I know that the number of rows in a table is 1, and the number of blocks in the table is 1 million, and I have a query that can get a row out of that table using an index, I'm probably going to want to use the index to get that, because there's 1 row in the table, but there's 1 million blocks. So if I full scanned, I'd have to full scan lots of information. Using the index, I'll be able to find or not find the record very efficiently. But just having this basic information gives you enough data to start writing your optimizer. Index statistics. These are automatically gathered during index creation and maintenance, and include things like the number of leaf blocks, branch levels, clustering factor. An important thing to know, since Oracle 10G, anytime you do a create index or an alter index rebuild, you have already computed statistics on that index. I point this out because I've seen a lot of people come in and they drop their tables, they create their tables, they load them, they index them, and then they gather stats with an estimate percent of 10, and cascade gets true. And what that means is they took their statistics from the index create that they already had, they deleted them, and cascade gets true, and then replaced them with a 10% sample. Just make sure that you're not accidentally getting rid of something you already have. Remember, after a lot of create or rebuild, your statistics are already going to have accurate stats associated with them. I do like to point out that in version 12, tables with the estimate will have basic statistics gathered during loads as well. In version 12, if you do a create table list select, or you do a direct path load, insert append into an empty segment, we will have already computed all of these statistics for you. This can greatly reduce the amount of statistics gathering you do after a data load. Load an empty segment and you index that empty segment. You already have all of these statistics gathered. You might have to go pick up some histograms on certain columns, but that's all you'll do. So you can significantly reduce the amount of statistics gathering you do. Now let's talk about histograms. Histograms are used with skewed information. They help the optimizer figure out correct cardinality estimates. Since version 10 of the database has been spying on you, watching you. When you run a query and select star from table where x equals 5, the database is going to remember in the dictionary that you use column x all of the equality. So where y is greater than 10, it will remember to use y. Now let's talk about and so on. When we go to gather stats, if you let the method opt parameter default, we will use this information. In fact, it's use x and y in a where clause to determine whether or not we want history. Whenever you use a column in a where clause, and that column has skewed information, some of its values points to lots of rows, some of its values point to very few rows, the optimizer would like to be aware of that, would like to know those numbers. So you use this default method. As you run queries, you track the columns you use in the where clause. When you gather stats, we look at the columns you use in the where clause, and then we sample the information in those columns. If that information is in fact skewed, we automatically generate a histogram for you. You want histograms from columns that are used in where clauses that contain skewed information. It doesn't matter if they're indexed or not indexed, or anything else like that. It just matters if A, I use them in a where clause. I use them in a where clause, I need to be able to estimate the cardinality.
Debería tener con autofoco, supuestamente.
Now, in 11G and before, there's two
El
types of
autofoco.
histogram, frequency and a height balance.
Cuando pone autofoco se deshabilita.
You could also refer to these histograms as
Si le pongo,
kind of
deshabilita.
histogram, the bad kind of histogram. A frequency-based histogram is a histogram that's created on a column that has less than 254 distinct values. A histogram has a series of buckets associated with it, a set of rows, and these rows are limited to 255. You need to have 254 or less distinct values in it.
Debe ser
Now,
un
we can create what's known as a frequency-based
Sí,
histogram.
pero mucho son.
In the frequency-based histogram, each one of these buckets, each one of these rows will represent one value in that column.
Yo traía la cámara digital profesional, ahí la tengo, pero tuve problema de hacerle funcionar, pasarle el video. A esta no va a funcionar.
X has a frequency histogram on it. We'll go right here to X equals 5 and see exactly how many records that's going to return. Get a very perfect estimation, if you will, as long as the stats represent the data. There is also a height balance histogram. In a height balance histogram, these get generated when we have more than 254 distinct values. And in a height balance histogram, a single popular value can be found in one or more of these buckets. So we have 254 buckets. A really popular value, value of a column that points to millions of rows, they consume actually more than one bucket inside the histogram. And that's how we generate, that's how we store the fact of how many rows are actually pointed to by that value. And what happens is you got the 254 buckets, if you have a few really popular
Somos
values,
compañeros, digamos.
those guys will use up lots of those buckets, leaving very few buckets for the other values. And remember, the other values number above 254. So there's hundreds or thousands or millions of these other values. What tends to happen on the height balance histogram is the values that are really popular, the values that point to most of the data are encoded in the histogram. We can accurately estimate their cardinality. For values that are very unpopular, they only point to one or two rows, they would never make it into this histogram. We'll run out of buckets way before we get there. Then there's another class of column values. Column values that point to a lot of rows, but not nearly as many as the really popular ones. And the really popular ones will take multiple buckets. And so these almost popular values get pushed out of the histogram. They're not represented in there. You don't see them. And you end up getting a bad cardinality estimate for them. So the height balance histogram in general would be really useful.
¿Se le sacó eso? ¿Escucha mejor? ¿No?
Transmite él.
Está sonando como dos micrófonos.
Pancho, mira, para almorzar está acá abierto el cocina acá y hay varios menús,
Ya.
hay una estofada, tallerías, qué sé yo.
One of two new types of histograms. The first one is called a top frequency histogram. Remember, a frequency histogram was considered to be a good histogram because a frequency histogram had a bucket per value, and we knew exactly how many rows had that value. But it only worked if there were 254 or less values. With the top frequency, what they've said is if a small number of rows points to 99% of the data. So if I can find a set of column values such that those values, if I retrieve all the data that has that value, I'll get 99% or more of the table. And if the number of those values is less than 254, what I'll do is I'll create a frequency-based histogram on them. So I'll take the 254 data values that point to 99% of the data and put those in a top frequency histogram. And for the data that points to the remaining 1%, that could be hundreds or thousands of other data values, we will leave them out of the histogram. The effect of leaving them out of the histogram will cause their cardinality estimate to be very small. We know their cardinality estimate is very small because they point to way less than 1% of the data. But everybody else who points to the 99% of the data in the table, you'll have your own bucket in the histogram. So we'll be able to encode all of the popular and almost popular values with exact row counts, and we just ignore the rows that point to one or two, we ignore the values rather, that just point to one or two rows in the table. So we get all of the benefits of a frequency-based histogram, even though there's more than 254 values. But again, this will only happen if you let estimate percent default to auto sample size. So it would be even more important in version 12 to be using the default for estimate percent. Another one is called a hybrid histogram. It's similar to a height balanced histogram, but it limits the buckets a value can take to 1. In a height balanced histogram, an individual data value might have crossed multiple buckets. The more rows it pointed to, the more buckets it consumed. In this hybrid histogram, that really popular value will be limited to 1 bucket. That will allow us to encode many more values into the hybrid histogram. So we will encode all of the really popular values, ones that point to most of the rows, and we will be able to encode most of the almost popular values. We will still leave out the unpopular values. They will not be represented in the histogram. Their cardinality estimate will be low, which is correct. They point to few rows. The almost popular values will appear in there, and we'll have the correct cardinality estimates. And the very popular values will appear in there as well. And again, that's only with auto sample size. If you're gathering stats with auto sample size in version 12, you will eventually see all of your height balanced histograms disappear as they're regenerated, and you'll get either a frequency, top frequency, or hybrid. If, on the other hand, you're running a version 12 database for 2 or 3 years, and all you have are height balanced and frequency-based histograms, then you know that somebody's gathering stats with a non-default estimate percent, like an estimate percent of 10, and it's time to have a talk with them to stop doing that. They're using your algorithms from version 10 in version 11 and 12 if they specify an estimate percent. So why do people sometimes hate histograms? There's 2 common issues with it. One is bind peaking, and the other one is those nearly popular values prior to version 12 having histograms. But what about this bind peaking thing? How many people in the room are aware of the words bind peaking and understand what the issue is? 1. Hopefully a lot of people are just being shy. They know about this. But let's walk through a quick example. So let's start from the table where x equals question mark. We just started our database. Okay? So there's nothing in the shared pool. Every query is going to be a hard parse. You're hard parsing this query, so let's start from t where x equals question mark. You're the optimizer. You went through the syntax check, the semantic check, the shared pool check. You found nothing. As I said earlier this morning, you wait for the program to give you the bind variable values. You don't optimize yet. So you wait for them to call the bind routines, and they bind the value of 10 to x. So the query is going to be where x equals 10. Okay? Now we go to optimize. With bind peaking, what the optimizer does is it takes the bind variables the developer used to execute that query, and it plugs them into the query, and it optimizes the query as though it had those literals in it. So instead of optimizing select star from t where x equals question mark, we're going to optimize select star from t where x equals 10. So the optimizer would go to the statistics, and it would find out that table T has 1 million records in it. It would find out that X has 10 distinct values. Okay, so right now by default, estimated cardinality for where X equals 10 would be 10 into 1 million for 100,000 rows. But further, we have a histogram on X. So it goes to the histogram, and since X only has 10 values, we're going to have a frequency histogram. So that's less than 254. So we go to the histogram and say, how many rows is X equal 10 going to actually return? I'm thinking it's 100,000 right now, but Mr. Histogram, can you give me better information? And the histogram says you're going to get 5 records back. Okay, so if we're going to get 5 rows out of 1 million, and column X has an index, what would you like the plan to be? Anyone? Use an index. 5 rows out of 1 million, almost absolutely want to use that index. You run the query, bam, it's great. Right? So that plan gets put up into the shared pool. You come along and you run select star from X where X equals question mark. So he ran the one with the index X equals 10. You come along and you run select star from T where X equals question mark. We do the syntax check, the semantic check, shared pool check. When we did the shared pool check, we found his query plan. Index range scan, table access, index ID. You now supply your bind variable. You supply the bind variable of 1, and we run the query, and you just pulled back 990,000 records. Aren't you a little disappointed? Because what you did was you went to an index 990,000 times, got a row ID, went to a table, got a row, sent it back. Went to the index, got a row ID, went to the tables, got a row, sent it back. Index, table, index, table. You got over 99% of the table back through an index. That's not a very good plan for you, is it? But that's what bind peaking does. In version 9 and 10, that would be the end of the story. In versions 9 and 10, the first person to hard parse the query would put a plan into the shared pool that everyone would share. He put the index plan in. You got stuck with the index plan. You want to have full scan. It's next week. You shut down the database to do a backup or something like that. You started it up. The shared pool's empty. For once, you guys beat him into work. He usually comes in first, but you get there first. Now you guys come in and do the same select star from T where X equals question mark. Syntax, semantic check, shared pool check. Don't find it. We wait for you to bind. You bind X equals 1. You go to the optimizer, and the optimizer says, histogram, what will X equals 1 return to me? It says 990,000 rows out of 1 million. I want a full scan. You build a full scan plan, you put it into the shared pool. What happens when he runs his query with X equals 5? Or X equals 10? He's going to get 5 records, but how is he going to get 5 records out of 1 million? Full scan, and it's your fault. You did it to him because you came in first. Right? And later on, that query plan gets aged out, and he runs it first. He gets the index in. You were happy all morning, but you know you're sad all afternoon. And he's very happy. Right? And then something else happens, and the plan ages out, and you're the first ones to parse it. You're really happy again, and he's really, really sad. Right? So that's bind peaking. And it was problematic in versions 9 and 10, because whoever got the first plan in sort of wins. In version 11, we changed the algorithm. We introduced a thing called adaptive cursor sharing, so that if we discovered a single plan wasn't good enough, right, we could actually develop multiple plans for different sets of bind inputs. So he would be able to get his index range scan, and you would be able to get your full table scan. So this is how it worked in 9 and 10. The initial value binds to Sherman's plan. That same execution plan was shared regardless of future bind values. Potential for plan changes when the first value peaked is popular or unpopular. If you guys hard parse first, full scan. If he hard parse first, index range scan. So it's dependent on who used the application first, what plan would be there. So this is bind peaking in histograms prior to 11G. We have a query where depno equals : depno. We have a count of employees that they maximum. Well, there's 10 employees in this table. The max depno is 99. If the bind value of depno equals 9 at hard parse time is observed, we're going to estimate that we're only going to get 10 records out of here, and we're going to go with an index range scan. So the first time this is executed, somebody ran it with depno equals 9, and 10 records was assumed to come out of this. 10 records out of all the records in the table, well, we're going to index range scan, table access by index row ID. Later on, somebody runs a depno of 10 at hard parse time. Well, that's the same exact query. We would like to see a full table scan because that's going to get 99,900 records out of this. Depno 10 is very popular. Depno 9 is very unpopular. But what would happen with bind peaking in versions 9 and 10, one or the other of these plans would be chosen, and everybody would use it for all subsequent runs. Now, what could you do prior to version 11 when you ran into bind peaking problems? One is you could drop the histogram on that column, and you could set a table pref saying don't gather that histogram in the future. But what's that going to do to us? You know, if we assume that there's 1,000,000 rows in this table, right, and depno equals 9 gets 10 of those records, and depno equals 10 gets 99,900 records. If there's 1,000,000 rows in the table, and there's, say, 10 distinct values of the depno, and we don't have a histogram, what is the optimizer going to estimate as its cardinality? 1,000,000 rows, 10 distinct values, no histogram. The estimated cardinality for this where clause will simply be 1,000,000 divided by 10. It will assume that every query will get 100,000 records, and if every query gets 100,000 records, every plan is going to be a full scan. I'd say that sounds like a bad idea. What you've done, though, is you've made it so that the optimizer can only give you one plan. If it runs with an input of 9, that will be 100,000. If it runs with an input of 99 or 10, that will be 100,000. You get the consistent plan. And if you get a consistent plan, you can probably come up with a way to get a consistent plan that you like, right? You could do something like use a stored outline in version 9. Maybe you could use a hint. I'm going to try to dissuade you from using hints. The last section I do today is the section everybody came for. So if you skip any of this session, don't skip the last half hour, because I'm going to show you how to fix queries by magic, literally. You can fix a plan without touching the application, without touching the SQL, without having to use hints. But if you got into a situation where you're getting the same query plan for the query over and over and over again, I'm pretty convinced most of you could come up with a fix to get the plan you actually want, right? You want to get rid of the instability. Getting rid of the histograms will give you a consistent plan. If it's not the plan you wanted, you have techniques for getting the plan you want in it. Set the parameter to change the default method up to prevent the histogram from being created in the future and regather the statistics on it. There could be cases, though, where you have an application where some sets of queries need the histograms because they're not using bind variables through reports and such, and you want the histograms. You can switch off bind peaking. This isn't undocumented in the .log parameter. I'm not real big on setting that, but what you can do is set that at the query level. There's an optimizer hint that you can stick in there. I'm going to demonstrate it in the section on hinting, but it allows you to turn on and off specific optimizer parameters on a statement by statement basis. So in a statement that's having bind peaking issues, we can actually disable this. I would not want to do it at the system level. I would not want to do it at the application level, but rather just tell the one or two queries that are having an issue with bind peaking, don't do bind peaking. And I'll show you how to do that in a couple of minutes. With adaptive cursor sharing, this is version 11. We can have both plans for statements in there. If depno equals 10 or depno equals 9 should estimate 10 rows and give you an index, and depno equals 10 should estimate almost 100,000 rows and give me a full scan, this is ultimately what I'd like to see in my shared pool. Right? If you use selected bind inputs to get small numbers of rows, use this plan. If you use bind inputs to get large numbers of rows, use this other plan. So we'd like to have the ability to have both these plans in there. And so what happens is we're going to be able to share the plan when the bind values are equivalent, meaning the optimizer is going to look at the bind value you supplied, and it's going to say, this gets me a small number of rows, or a medium number of rows, or a large number of rows. It's going to be placed into what we call a selectivity range. And then that selectivity range will be associated with a query plan. When I go to find a query in the shared pool, my bind variable value will be placed into one of these selectivity ranges, and I will find the plan that has that same selectivity range. So if I came in with depno 9, I would be looking for the plan that returns a small number of rows with this bind variable. If depno equals 8 was estimated to return 5 or 6 records, it would get the same plan as 9. Now depno 10 gets 100,000 records, so that's giving a lot of rows. Depno 20, if it's assumed that gets 100,000 records, it would get the same plan as depno 10. But depno 40 gets 0 records. Nobody works in department 40. That would get associated with the same plan as depnos 8 and 9, because they get small numbers of rows. So it's not that we'll have a separate plan for each bind input, but rather we'll have a few plans for these selectivity ranges, and many bind inputs will share it. How to monitor this? $SQL has 2 new columns, is bind sensitive and is bind aware. And this will show you cursors that are subject to this adaptive cursor sharing. We'll go through step by step. We're going to set the bind variable to 9. Remember, that gives a few number of rows. And we're going to run that query with the bind variables. The execution plan from $SQL plan shows that we're using an index range scan because we estimated 10 records. If we look in $SQL and we look at is bind sensitive, is bind aware, we can see that that cursor we just created is bind sensitive, but it's not aware of a problem yet. So when you see a column that has is bind sensitive set to yes, that's a cursor that's been marked by the optimizer during the optimization saying, there's something in this SQL query, there's something in this where clause, that if you sent me really different bind variables, I would come up with a totally different plan. So all that yes means is there's definitely more than one plan possible for this query based on the bind variable sent to me. So I'm sensitive to these bind inputs, but I'm not aware of a problem yet. Okay, so now we run the query with depno equals 10. The way this works is we're not aware of a problem, so we're going to give it a chance. This first execution, depno 10, is actually going to use the index range scan. It's going to use the existing plan. Because remember, We're sensitive to bind inputs, but we're not aware of any problems yet. So we ran a query. And now we can see the number of executions is 2. We're bind sensitive, but the buffer gets went from like 3. This is what we were expecting, right? Because if you look at the query plan, we're expecting to do an IO against the index and 1 or 2 IOs against the table. We're expecting to do like 3 IOs at most to run this query, but all of a sudden we did 957. If we take the average number of IOs, 957 divided by 2, we're doing an average of 500 IOs per query now. We're expecting to do an average of 3. Our expectation has not been met. This is what flags the runtime engine. It's okay. You told me to watch this query because it's sensitive to bind inputs. I have now just detected a problem. I was expecting this to be 6, not 500. Or I was expecting it to be 3 per execution, not 500. So what will happen is the next time we run it with that nu equals 10, get the same answer, but we'll have a new child cursor now. And they will have the full scan plan. If we look in $SQL, we'll see that there's a bind aware plan. It's aware and it's sensitive to bind. This is the query plan for non-selective bind inputs. If I were to run the other query with get no equals 9, it would create a new child cursor having yes and yes, and it would have the index range scan. This cursor up here, the one that we were using just a minute ago, it's invalidated. It can be aged out of the shared pool. It might even disappear at some point in time. We're not going to use it anymore. But for each range of bind inputs, we're going to create a new child cursor. And so if detno 9 came along, we would actually create that second child cursor. Nearly popular values. So these are the guys who are problems in a height balanced histogram. The concept is you have more than 254 distinct values, so you don't have a frequency histogram. You have some really popular values, but they're so popular that they consume the entire histogram. You have some unpopular values that don't make it in the histogram. That's okay. You come up with a very low default cardinality estimate. But you have this big set of almost popular values. They point to hundreds or thousands of rows, not millions, not 1 or 2. They point to a lot, but not quite as a lot as the really popular ones. They don't make it into the histogram because the really popular guys crowded them out. Therefore, we underestimate their cardinality. We assume that since we don't see them in the histogram, they have a very low cardinality associated with them. So what is a possible solution for this? So in this case, we have a customer city ID 52114. It returns 227 rows, but we have a very low default estimated cardinality for it. And when the estimated cardinality is off by orders of magnitude, this is off by 1 order of magnitude, that's when we start having a bad time with our query plans. We would like this number to be within an order of magnitude of that number. But this is one of those almost popular values. It's not in the histogram. The default selectivity is not good enough for it. What we can do is run this with a dynamic sampling hint. Now, you might look at this and say, we're running it with a dynamic sampling hint at level 2. Many of you might know that the default dynamic sampling level in Oracle 10G and above is set to level 2. There's a difference between the session setting of 2 and hinting at level 2. Hinting the sampling at level 2 is stronger than just having the session set to level 2. When I hinted it to be level 2, basically I was telling the optimizer, anytime you're guessing based on insufficient statistics, I want you to sample the information quickly to validate that guess. And so what happened here was we took 52114 to the histogram. We couldn't find that value in the histogram, So we defaulted its cardinality based on rules, basically, based on densities. We guessed. When we guess, when we're at dynamic sampling level 2, we'll do a sample scan to go out and validate that guess, and we adjusted our estimated cardinality based on that sample scan. We said we estimate there's 248 rows for this, which is pretty close to 227. It's much closer than 66 was, right? And so in version 11 and before, this would be a way to correct a Heights balanced histogram that wasn't giving you good cardinality estimates on almost popular values. Now, if I had run this query with a very popular value, it wouldn't have dynamically sampled because it would have found the value in the histogram. It's only when it doesn't find the value in the histogram that it would feel compelled to go out and sample the data to validate its cardinality estimate. In version 12, this will not be necessary anymore because in version 12, we'll have encoded those almost popular values either in a top frequency or in the new hybrid histogram. So this is something that would apply to versions 9, 10, and 11. And this is a very safe hint to put in here. It's what I call a good hint because it's not telling the optimizer how to run the query. It's giving the optimizer more information, saying if you have to guess, you're free to go and look at the data in the table to validate that guess and adjust your guess based on what you see. Okay, so it makes the parse operation take a little bit longer, but hopefully that results in a better plan because these estimated cardinalities will be correct. Some additional statistics, column groups and expression statistics. I'm going to make people raise their hands again and see how this works. In this room, how many of you were born in the month of December? Please raise your hand. If you were born in December, exactly 112. Perfect. How many of you in this room are the zodiac sign Pisces? Raise your hand. Zodiac sign. Exactly 1 out of 12 again. Perfect. Now, will all of the Pisces born in December please stand up? I'm a Pisces, but I was born in March because all Pisces are born in February or March. There's a relationship between your zodiac sign and the month of birth. Does the database know about that relationship? No. If I have a date column in there, and I find 1 out of 12 people fall on a given date, and I have another column, the zodiac sign, and I find 1 out of 12 people fall in that zodiac sign, and I say, give me all the Pisces born in December, what do you think the optimizer is going to guess? It's going to take the probability of being born in December, it's going to take the probability of being a Pisces, it's going to multiply them together. It's going to assume that 1 out of every 144 records in that table are Pisces born in December. How many is it really? 0, barring any data errors, right? But it should be 0. But they're going to guess something like 1/3% of the table is going to come back, right? And if the table's got a lot of rows in it, that's going to be a big number. There's lots of real-world correlations between things. How many pink BMWs have you seen? Not too many. How many dark green BMWs have you seen, or blue, or black? Lots. If you have an Audi, odds are it's black or dark silver. If you have a Volkswagen Beetle, odds are it's yellow, lime green, pink, something like that. There's a definite correlation between the type of car you have and what color it is. I used to drive a Toyota Prius. Over 90% of Priuses are white. If you have a Prius, it's almost certainly white. If it's not white, it's gray or red, and that's about it. Right? So there's a big correlation between those two things. Database is not aware of that by default. Extended statistics in 11G make the database aware of that. It allows us to gather statistics on groups of columns simultaneously. I have really good statistics on the car make and model. I have really good statistics on the car color, but I don't know anything about the two of them simultaneously. That's where these extended statistics and expression statistics will come in. So let's take a look at this. Select car for vehicles where the model equals 530xi and color equals red. The way the database will estimate these cardinalities is we'll take the number of rows in the table, multiply that by 1 over the number of distinct values in column 1 times 1 over the number of distinct values in column 2. When you do this math, it gives us an estimated cardinality of 1, which in this case was perfect. However, let's look at a query where model equals 530xi and make equals BMW. This gets a little bit tricky. How many 530xis are made by Toyota? None. Audi? None. Mitsubishi? None. Who makes a 530xi? BMW. They're pretty much the only ones that do. If we take the probability of being a 530xi and we multiply it by the probability of being a BMW, what would happen to our estimated cardinality? It will go down, right? Because the probability of being a BMW is less than 100%. But if I'm a model 530xi, I already know I'm a BMW. This where clause is going to underestimate the cardinality just by default, right? Because we're going to take the number of rows times the probability of being a 530xi times the probability of being a BMW. And we estimate it 1 row, when we really got 3. We should not have multiplied by this 1/3 because everything we needed to know was right here. But the optimizer has no idea about that, right? I mean, you know because you're humans and you read newspapers and you look at cars on the street and stuff like that. But the database doesn't have any of this information. So what we can do is create extended statistics on the vehicle table for model, column, make. What this will do is gather stats in these 2 columns simultaneously. And it does this by adding an invisible column to our table. So this is actually a column name. It's a column that's now added in our table. The next time we gather stats, we're able to have that column potentially appear. Now, we've added this extended statistic. We've gathered stats, but notice there's no histogram on this guy yet. When will stats gathering create histograms for us? Earlier this morning I said we've been watching your where clauses, and we record when you use a column in an inequality in a range and put it in the data dictionary. We just created this brand new column, but we haven't used it in a query yet. So by default, we won't have those histograms. So we go ahead and we run that query. The next time we gather histograms on this, that column would actually have a histogram generated because it would have seen us use the model and the make. And then we would end up getting the right estimated cardinality. So you might have to create the extended statistic, not only gather table stats, but actually run your query at least once so that the next time you gather stats, it picks up the histogram on that column for you. Right? So until we actually use this column, you don't have to reference the column by name. All you have to do is say model and make. We will record that as you having used this sys underscore column. The next time you generate statistics, we will have histograms generated on that for you. The alternative would be to gather table stats, say for all 4 columns, and then plug this name into it. explicitly gather the histograms on that column right then and there. And then we would continue to pick up those histograms into the future. Expressions. Select star from the table where the quantity of A plus B divided by 2 is greater than 50, where the average of A and B is greater than 50. What's an optimizer to do with that one? You have tons of information on A, you have tons of information on B. What's your estimated cardinality for the average of A and B? You're going to guess. And you're going to guess 1%, or you're going to guess 5%. For an expression like A plus B divided by 2, you're going to guess 5%. For a function on a database column, you're going to guess 1% of the rows. Because you have no idea. This is the upper of customer last name. You know a lot about customer last name. You don't know anything about the upper of customer last name. So you're resulting to a guess, resorting to a guess. And you know what's even worse is if you said where upper of customer last name equals Smith and upper of customer first name equals Tom. So now I have 2 parts in my where clause. Each estimates 1% of the rows in the table. So when I put them both together, how many rows would it thinks are going to come back from that? Because it will take 1% of 1%. It would estimate 5 rows. It was estimating 555. And if I said where upper of customer last name equals Smith, upper of customer first name equals Tom, and upper of customer middle name equals Jeffrey, it's going to guess 1% of 1% of 1%. It's going to guess less than 1 row. It's going to round that up to 1 row, and it's going to assume 1 record's coming back for that. You very quickly get to the single-digit cardinalities by having lots of functions of database columns. Right? So every time you put a function on a database column, you don't have statistics on that. You're going to be using rules to come up with the estimated cardinality, and it's going to be a 1% guess. So, for example, I can come and create an extended statistic on the upper of customer last name. It generated the histogram for me. It has the same num distinct as the actual customer last name had, but I basically have the same information statistically on the upper of customer last name now that I did just on customer last name. So when I go to do my cardinality estimates, I'm going to get much better cardinality estimates for that. I'll get the same cardinality estimates I would for the unfunctioned database column. So half the people in here said they were DBAs. How do you know what columns to create extended statistics on? How do you know what expressions? Do the developers actually come to you on a regular basis and give you this information? Or are you just supposed to figure it out? We're supposed to figure it out. One way to figure it out is to use this API, dbmastats seed call usage. For the next 300 seconds, the database will watch the queries not only record the single columns you use in your where clauses, but it will look for column groups as well. So we've called seed call usage, and we do a city, state, and country query. Looking at this where clause, and based on the information I gave you this morning, you should be looking at that and saying, oh, I recognize that. That's going to give me an incorrect low estimated cardinality. Because you can just look at it now and say, you know, if I know what the city is, I know what the population of that city is. If you say city and state, well, that's going to take the probability of being in Los Angeles and multiply it by the probability of being in California. But all I needed was the probability of being in Los Angeles, right? Because there's not too many Los Angeleses outside of the state of California. And Los Angeles, the state of California, is so huge. This is the estimated cardinality of these. This is going to lower it. And this is going to lower it even further. This must be the country ID for the US. Well, California is in the US. So if we let the optimizer do its default sort of thing, it's going to take the probability of the city times the probability of the state times the probability of the country. It's going to come up with a low number. It should have probably just been the probability of the city. The database doesn't know this. So this is a problematic query. Well, we run this. So the database observes that we use city, state, and country. We run another one. We don't have any where clause, but we did group by country ID and customer state province. Figuring out cardinalities for group bys is pretty hard, right? If you know the number of distinct values for one column and the number of distinct values for another column, that's really not enough information to figure out the number of distinct values that can come out of this group by. After the 300 seconds is up, we can report on the column usage. And this is just simply printing out a report in SQL Plus or SQL Developer. These first three have quality predicates. These were always being picked up since 10G. So this morning when I said we were spying on you and we were saving stuff in the dictionary, we picked up on the fact that you use country and city and state as qualities. The C call usage picked up on the fact that you use these three columns together. So these were in a where clause against a single table, and we used them together. This is a candidate for creating extended statistics. We're going to have stats on country, city, and province. If these guys are skewed, that will generate those histograms. Now, if we generate extended statistics on this column group, we'll get that same information, but about those three columns, not each column independently. And it also noticed that we used a group by on these guys. And it would be interesting to understand the number of distinct values in the customer state province, comma, country ID. If that information was skewed, we'd like to understand that so that we can see that different group by sets would have different estimated cardinalities. We'd be able to come up with better estimates. And so what you could do as a DBA is just simply create extended stats from this information. And it will go ahead and take that one column group, create the extended statistic, take the other column group and create it. And now those column group statistics will be automatically maintained as part of your DBMA stats gathering routine. What's the difference if I create an index by those three fields? And you have a histogram and an index. No. The only thing you would know is NDV, number of distinct values. So it used to be in the olden days, before extended statistics, trying to get a little bit more information to the optimizer, we would create a function-based, or we could create an index on those columns, or we could create a function-based index, gather stats on that. But that didn't give us basic column statistics or histograms. Right? It gave us index statistics. And in general, it gave us index statistics on indexes we didn't even care about, that we didn't want. Right? So this is far superior than trying that index trick. If you're in version 9 or 10, you may need to play around with that index trick. Just get into version 11, drop that index, and replace it with extended statistics. Much lower resource utilization. I don't have that index to maintain, and I have all of the column statistics that I need, histograms specifically. Because creating an index on city, state, and country won't help me figure out that I really only need the probability of the city to get the estimated cardinality. It'll tell me the number of distinct values in the column, which is something in the 3, which is something I didn't have before, but I don't have any other column information, like histograms specifically. But valid question is, that's a technique that we used in the olden days, but should be forgotten about as we migrate to these extended statistics. This gives us the number of distinct values, but it also gives us the histograms as a potential as well. When to gather statistics. This seems like it should be an easy question. When should we gather statistics? There should be one answer, right? There is one answer for every different set of circumstances. There is this automatic job that we run, which for many people is adequate. Runs in the maintenance window. It prioritizes what tables to gather, tries to get as many tables as it can within that window, and then it stops running and it goes ahead and does it the next night. In a data warehousing environment, that auto job is useless. Should be totally turned off. In some other OLTP environments, high-end OLTP environments, many people turn off the auto job and they program it themselves. But the auto task works for many people in many cases. Just understand how it works. It will wake up at the beginning of the maintenance window. It will discover what tables are stale. It does this by looking at what tables have had about 10% of their information modified by default. You can play with that 10% number, table by table basis, and it will prioritize those tables and segments that it wants to analyze based on how long they've been stale. So if there was a table that was stale last night that I didn't get around to doing last night and still stale tonight, that would be a higher priority table on my list of work to do than a table that just became stale this evening, right? So the longer a table has been in the stale state but not analyzed, the further up in the queue it will go. So this is a pretty good algorithm for most people. However, sometimes you need to override this for certain things. Let's say you have a table called orders. And this orders table grows at a rate of 10,000 records per month, every single month. And this table has 1 million rows in it right now. 10% of that table is 100,000. So I analyzed the table on December 31st, last day of the year. It's got 1 million rows in it. When is that table next going to be analyzed? Next month we add 10,000 records, so 10,000 records have been modified. It's not 100,000. Then we add 10,000, that's 20,000, 30,000, 40,000. It's not going to be analyzed again until October. But what happens when you run a query in June that says, how much stuff did we sell this year? What is the optimizer in June going to estimate the cardinality for that query? How much stuff did I sell this year? You know what the answer is because every month we do 10,000. It's January, February, March, April, May, June. It's 60,000. But what is the optimizer going to estimate? Anybody got a guess? I'm not going to let you go to lunch until you guess. No guesses? It's going to guess a very small number. Why? Not even 10%. It's probably going to be about 333. It's going to guess a very small number because the high value for the order date is December 31st. And we're sitting out here in June. We're far above that high value. And that table is not going to get analyzed for another 4 months. Might you need to, this is when you call up support and say, wow, we're getting full scans when we should be using indexes or vice versa. Optimizer's going wacky, and they say, when's the last time the table was analyzed? Oh, those look stale. Analyze the table. Fixes the problem, right? What's going to happen? 6 months later, you're going to be back on the phone, right? And they say, analyze the table. Good. Fixes the problem. Sometimes this little generic method doesn't work for some tables. Some tables need to be gathered much more frequently than some other tables do. If you have tables where you have columns that are populated by sysdate or sequences, and you use those columns in where clauses to estimate cardinalities, you're probably going to have to gather statistics on those tables more frequently than this algorithm would suggest. One way you could achieve that, you could change the default staleness on that table to 1%. So instead of waiting for 10%, just wait for 1%. That would be one approach. Another approach would be for you to set up your own job to gather stats on that table frequently. But bear in mind, as soon as you gather stats on the table, what is also true about the stats on that table? They're immediately stale. As soon as you're done gathering stats, somebody else has inserted a new row and the high value has advanced. Right? Maybe instead of you gathering stats on this table over and over again, you just understand the table grows rather slowly. If I could only tell the optimizer what the new high value was, everything would be okay. You can do that. You can go dbm stats.set column stats. You can supply a new high value. At the beginning of every week, set the high value to the end of the week, and you're good for the week. And it takes like a millisecond. Right? So you can actually fix the statistics on certain types of things. It does require you having a knowledge of your data, though. Right? You have to understand how the data is used and what parts are used in where clauses. But a lot of frustration people have with the auto job is it works on 99% of the stuff and it fails miserably at 1% of the stuff. So rather than trying to figure out the 1%, they just shut it off entirely and program the whole thing themselves. But the auto job in most cases can work nicely. There will just be exceptions to it that you have to look into every now and then. And perhaps you're going to gather stats on that table more often. Perhaps you're going to use dbm stats.set column stats to advance that high value. Those are two perfectly valid approaches. Oh, and if you do turn off this task, bear in mind that it was responsible for gathering statistics on your tables and on our tables. If you turn it off, which you can do in Enterprise Manager, and most people just totally disable it, and they write their own statistics gathering job, they typically write that stats gathering job to gather stats on their tables, not Oracle's tables. So what we would recommend is instead of disabling this job, you can set the job to be Oracle only. So the auto job will still run in the maintenance window. The only tables it will look at is the Oracle data dictionary. As the number of objects grow, as the number of segments grow, as the number of PL SQL packages grow, and things like that, the stats in our data dictionary need to be updated. If you just disable this job, you stop gathering those stats. You need to make sure that those stats get gathered, either as part of your job or let the auto job take care of it. So instead of just disabling this job entirely, you can set a preference on this job so that it only gathers Oracle stats against the Oracle data dictionary. And so you do this with the auto stats target, auto. We decide what needs to be done. We're taking a look at the entire database, Oracle tables, your tables. Every table will be gathered against. This is going to look at what tables are stale. This is just going to say everything. We're going to try to gather stats on every single table in this database every single time. If we run out of time tonight, we'll start tomorrow night where we left off. Right? We won't always gather on the same tables. We'll gather on as many as we can, and eventually we'll gather all of them. Or Oracle. Statistics are gathered only for the Oracle dictionary table. This is what I would want you to set it to instead of disabling the job altogether. Right? Because this keeps our stats up to date, and then you can take care of your stats. What about in the warehouse, where you just loaded a bunch of data? Do you really want to wait 12 hours till the maintenance window comes along and gather stats? In a warehouse environment, get rid of the auto job, let it do the Oracle dictionary tables, but you're going to explicitly gather statistics as you do your loads. If you just loaded a new partition and swapped it into a table, you better gather stats on it right then, right there, right now. If you're in a transactional system, let's say you're in an order entry system where every period of time, maybe every week, you add a new partition, and that's what your application starts inserting into, we have problems with statistics on that new partition all of a sudden. Right? So every week you create a new partition, all the orders for that week goes into that partition. At the end of the week, you create a new partition and all the orders go into that. So it's a partition that starts empty, but grows rather fast. When do you gather stats on that? Or how do you maintain stats on that? One not smart approach is gather stats on that new partition like every hour as it's growing. That's a bad idea, because that's going to cause a lot of parsing and reparsing of SQL and a lot of resource utilization to gather the stats. A better approach in most cases would be to create a new empty partition. Now you know it fills up rather rapidly. So what we'll do is we'll take the stats from the last partition and copy them over. We'll pretend that the partition is full, even when it's empty. And I say, that sounds like a bad idea, because we're pretending it's full when it's empty. Won't we get suboptimal plans? The theory is, it doesn't matter what plan you run against an empty table. It's going to be fast, no matter what you do. However, if you take a plan built for a small table and run it against a big table, that could be a disaster. So using a big plan against a small table is almost always okay. Using a small plan against a big table is almost always a bad idea. This approach, where we take the stats, using deviant stats, copy table stats, copy them from source to a target partition, where it will do things like adjust min and max values for partition columns and copy over all the dependent statistics. This actually came from the Automatic Workload Repository, AWR. So they started this in 10G. In AWR, every new period of time, they create a new empty partition. What partition does Enterprise Manager query more frequently than any other? The current partition. We were having really poor performance on queries because the partition started out empty and it rapidly got not empty. At first, the query plans ran great, but after a couple hours, couple of days, the performance went down. So what they decided to do was, before we create a new empty partition, we're going to gather stats on last month's partition. We're going to create the new empty. We're going to copy those stats over, adjust high and low values for partition keys and things like that, and we'll run with that. And that's what AWR does every period of time. This is a tried and true sort of approach to that transactional partition table. When we come back from lunch, we'll talk about stats gathering performance, when not to gather stats, and other types of statistics, and then start the last section, which is all about query performance tuning. We'll be taking a look at hinting and how to hint, how not to hint, and basically what you want to be doing as you're tuning a query and how best to do that. And as I said, the last section, if you miss everything else, come back to the last half hour. I'll show you a bit of magic. I'll show you how to tune the query in a bit of code, given that you're not allowed to edit the code, change the query, change any system settings. You can't touch an init.org parameter. You can't resize the SGA. You have to tune that query and make it do what you want it to do. You can actually do that. It looks a little bit magical, but it's very straightforward. So I think we have about an hour for lunch, 12:30 to 13:30. And I'll see you back here in an hour. Join us. No sabe, no tiene ni idea lo que va a hacer. Ahora vamos a hacer. La Ceniciento, el Ceniciento. El día de la matación, pero de noche duerme poco, dice. Sí, sí.